Hey, what's all this about heat and things moving? It's science. Let's dive into thermodynamics and transport phenomena, the science of energy and movement. Thermodynamics is the rule book for energy behavior from atoms to stars. Transport phenomena involve how heat, mass, and momentum move, like stirring sugar into a drink or feeling warmth from a radiator. These concepts are crucial for designing efficient machines and processes. We'll explore the 4 laws of thermodynamics and how heat travels through conduction, convection, and radiation. Understanding these concepts helps solve real-world problems like building efficient engines and sustainable energy sources. Get ready to explore the science that powers our world. It's going to be awesome. Let's get started. First up, the Zeroth law of thermodynamics, which might sound a bit strange because it was named after the first 3 laws were already established. But don't let the name fool you, it's incredibly important. This law is all about thermal equilibrium, a fundamental concept in thermodynamics. If 2 things are each in thermal equilibrium with a third, then they are in thermal equilibrium with each other. This might sound simple, but it forms the basis for how we understand temperature. Essentially, it means that if 2 objects are at the same temperature as a third object, they must be at the same temperature as each other. This is why thermometers work so well. Thermometers rely on this principle to measure temperature accurately. By coming into thermal equilibrium with the object being measured, they give us a reliable reading. This allows us to measure temperature in a consistent and precise manner, which is crucial in both scientific research and everyday applications. Now let's move on to the first law of thermodynamics, also known as the law of conservation of energy. This law states that energy cannot be created or destroyed, only converted from one form to another. It's a fundamental principle that governs all physical processes. For example, when sunlight is converted into electricity by solar panels, or when chemical energy in fuel is converted into mechanical energy in a car engine. Think of a car engine converting chemical energy from fuel into mechanical energy to move the car, and heat energy as a byproduct. Engineers must account for all energy inputs and outputs in any system to ensure nothing is lost or unaccounted for. This balance is key to efficiency and preventing breakdowns. By understanding where energy goes, we can design more efficient systems. It's like balancing your energy checkbook. Every bit of energy must be accounted for to ensure the system runs smoothly. These laws are fundamental for designing everything from power plants to microchips. They ensure that energy is used efficiently, and systems operate as intended. Understanding them ensures systems operate safely and effectively. Let's keep exploring the fascinating world of thermodynamics. The second law of thermodynamics introduces entropy, a measure of disorder. Entropy increases over time, which explains why things naturally tend to become more chaotic and less organized. This principle is evident in everyday life, from the way your room gets messy to the inefficiencies in industrial processes, explaining why processes aren't 100% efficient. No matter how well we design machines or systems, some energy is always lost as heat due to increasing entropy. Heat flows from hot to cold, a fundamental concept that drives many natural and engineered processes. This is why your coffee cools down over time and why refrigerators need energy to keep things cold, and gases expand to fill containers. This behavior is crucial in understanding how engines work and how we can harness energy from fuels. This law is crucial for designing efficient systems and understanding energy loss. Engineers use this knowledge to improve the efficiency of power plants, engines, and even renewable energy systems. The third law deals with absolute zero, the theoretical temperature where all molecular motion ceases. At this point, entropy or disorder approaches a minimum. Absolute zero is unattainable, but understanding it is vital in fields like cryogenics. This knowledge helps scientists develop technologies that operate at extremely low temperatures, but understanding it is vital in fields like cryogenics. It allows us to explore new states of matter and develop advanced materials. It helps us understand material properties at low temperatures, like superconductivity. Superconductors have zero electrical resistance, which can revolutionize power transmission and magnetic levitation technologies. These laws complete our understanding of energy and its limits. They are fundamental to the development of new technologies and the improvement of existing ones. They guide engineers in creating efficient, innovative solutions. By understanding these principles, we can design systems that are more sustainable and less wasteful. Let's continue our journey through the fascinating world of thermodynamics. There's so much more to learn and discover about how energy shapes our world. There's so much more to discover. Onward! The future of energy and technology is bright, and it all starts with understanding these fundamental laws. How does heat move? This is a fundamental question in the study of thermodynamics and energy transfer. Heat, a form of energy, can move in several ways, and one of the most common methods is conduction. One way is conduction, like heating one end of a metal rod. When you heat one end of a metal rod, the heat travels along the rod to the cooler end. This happens because the particles at the hot end start to vibrate more vigorously. Heat transfers through direct contact of particles like a microscopic hot potato game. These vibrating particles bump into their neighbors, transferring some of their energy. This chain reaction continues, passing the heat along the material. Metals are good conductors due to free electrons, while wood and plastic are insulators. Free electrons in metals move easily, carrying energy quickly from one part of the material to another. In contrast, insulators like wood and plastic have tightly bound electrons, making it difficult for heat to pass through. Engineers use Fourier's law to calculate heat transfer, considering area, temperature difference, and material thickness. This law helps in designing systems that manage heat effectively, ensuring safety and efficiency in various applications. Understanding conduction is crucial for designing heat sinks, insulation, and more. Heat sinks are used in electronics to dissipate heat, while insulation materials are used in buildings to keep heat in or out, depending on the season. It's all about managing that atomic hot potato game to our advantage. By controlling how heat moves through materials, we can create more efficient and effective systems. Engineers use this knowledge to create efficient systems and devices. From cooling systems in computers to thermal management in spacecraft, the principles of conduction are applied in countless ways. From electronics to building insulation, conduction plays a key role. Proper thermal management ensures that devices operate within safe temperature ranges, preventing overheating and extending their lifespan. Let's keep exploring the fascinating world of heat transfer. There are many more concepts and applications to discover, each with its own unique challenges and solutions. There's so much more to learn. Onward! As we delve deeper into the science of heat transfer, we'll uncover the intricate details that make this field so exciting and essential. Next up, convection, where heat moves with the flow of a fluid like boiling water. Hot water rises, cooler water sinks, creating convection currents. These currents are crucial in weather, ocean currents, and heating systems. Engineers use Newton's law of cooling to describe convective heat transfer. Convection is key for systems like car radiators and convection ovens. Engineers enhance or reduce convection to control heat transfer. It's like being a heat surfer, riding thermal waves. Understanding convection helps design efficient heating and cooling systems. From homes to industrial processes, convection is everywhere. Let's keep exploring the world of heat transfer. There's so much more to discover. Onward! Now radiation, where heat travels through electromagnetic waves like sunlight. Radiation doesn't need matter to travel, making it unique. Everything emits thermal radiation, increasing with temperature. The Stefan-Boltzmann law describes radiant heat energy. Engineers consider radiation in designs like spacecraft and solar collectors. Understanding radiation helps manage heat gain and loss. It's all about those energy waves. From toasters to buildings, radiation plays a key role. Let's keep exploring the fascinating world of heat transfer. Onward! Let's explore interfacial transport phenomena, where mass and energy cross boundaries. Think of boiling water, where energy and mass transfer at the liquid-gas interface. Membranes allow selective mass transfer, like water filters. Our bodies use membranes to control cellular exchanges. Engineers design systems to maximize or minimize transfers. In reactors, they maximize reactant transfer to catalysts. In distillation, they manage component transfer for separation. Fuel cell efficiency depends on ion movement across membranes. It's about managing microscopic border crossings for effective processes. Engineers use this knowledge to innovate and solve challenges. Let's keep exploring the world of transport phenomena. Onward! Material balance is like accounting for engineers, ensuring what goes in must come out. It's crucial for designing processes and analyzing systems. The material balance equation: input, output plus generation, consumption equals sign accumulation. At steady state, accumulation is zero, simplifying calculations. Material balances help determine raw material needs and equipment size. They ensure safety and environmental protection by tracking waste. It's meticulous bookkeeping for atoms and molecules. Engineers use this foundation for smart, responsible engineering. Let's keep exploring the world of material balance. Onward! We've journeyed through thermodynamics and transport phenomena, the principles behind engineering. From engines to power plants, these laws guide design and innovation. Understanding heat transfer mechanisms is key to controlling heat. Engineers use this knowledge to build efficient, safe systems. Managing mass and energy transfers is crucial for many challenges. Material balance ensures efficient, environmentally sound operations. These principles empower engineers to solve global challenges. Keep exploring, questioning, and learning to build a better future. Science rules.